Next we have this sixth one. Two sets are given A and B. A consists of 1, 2 and 3 and B consists of 4, 5, 6 and 7. And a function f is given from A to B like this. F has been expressed as a set. We can think of f as a set because a function after all is a relation. So it relates elements of one set to elements of another set. And the relation is this, which means that the value of the function at the input 1 is 4, its value at 2 is 5 and its value at 3 is 6, which if you express in functional notation, you would write f of 1, f with 1 within brackets is equal to 4, and similarly the other pairs. We have to prove that f is 1, 1. The solution actually is a one-line solution, but because you have to write something, so we can write like this. We see that f maps distinct elements of the set A onto distinct elements of the set B, and that is why f is 1, 1. But to elaborate a little more, that is, for any x1 and x2 in A where they are different, f of x1 and f of x2 are also different. That is why the function is 1, 1, because distinct inputs are not going to the same output. It's not 2 to 1 or many to 1, it is 1 to 1. That's the solution. So next we have the seventh one. There are two parts. Each part has a function and we have to decide whether that function is 1, 1, onto or bijective. In the first part, both the functions have the set of real numbers as both its domain as well as codomain. In the first part, the function is this, f of x equals 4 minus 3x, and in the second one, f of x equals 1 plus x squared. So let's solve this. So number 1 first. Here the function is 4 minus 3x. The output is 4 minus 3x if the input is x. So first we show that the function is 1, 1. It actually is 1, 1. So for that we take any two real numbers x1 and x2 such that the function values are equal. That means 4 minus 3x1 is equal to 4 minus 3x2, from which after some steps you already know the algebra. You are going to get x1 equal to x2, but when that happens, that your assumption that the outputs are equal gives you the fact that the inputs are also equal, then the function becomes 1, 1. So that's how our f is 1, 1. And next we see whether it's onto or not. It is onto actually. So for that what we do, we take any point y in R. Although both domain and codomain are R, here this R is considered to be the codomain. So we are taking any point from the codomain. And then we can think of this 4 minus y divided by 3, that's a legitimate real number. Whose f image is that chosen y? Because you can do the calculation and see for yourself. If you calculate f of 4 minus y divided by 3, it will be 4 minus 3 times that. So first the 3's will cancel each other, leaving you with 4 minus of 4 minus y. That means 4 minus 4 plus y or y. So that is why this f is also onto. And you have to write one more line, that being 1, 1 and onto, f is thus bijective as well. And next let us see part 2. This second function is neither 1, 1 nor onto. The presence of square in the function rule probably immediately tells you that it cannot be 1, 1, and additionally because the domain is R, so there are positive as well as negative real numbers. So you can use that fact to easily think of this. F of minus 1 is 1 plus minus 1 square, which becomes 2, but f of 1 is also 2 because 1 plus 1 square, although minus 1 and 1 are not the same number. So distinct inputs are giving you the same output. from both -1 as well as 1 you are getting the same output 2. That is why the function is not 1 1. And the function is also not onto, and that comes from the observation that it can never be negative. The values can never be negative again because of the presence of that square, although the codomain, which is also the set of real numbers, has negative numbers. If you find it, what should I say? If you find it convenient to write -1 here, you can do so. But for some reason I thought of writing 0 here. Just like 1 plus x square can never be negative, it can also never be 0. Why so? That is because no matter what your real number x is, its square is always non-negative. That means it's greater than or equal to 0. So if x square is greater than or equal to 0, if you add 1 to both sides of this inequality, what will you get? 1 plus x square is greater than or equal to 1. All the outputs are at least as large as 1. Not only are the outputs not 0, actually none of them is even less than 1. So you have many points on that side of 1 which are not outputs under this function of any input. So how can it be onto? So this function is the exact opposite to the previous one. It is neither 1 1 nor onto, whereas the previous one is both. It is bijective. And let me just end the video here itself. There are some other problems also that we will solve next week. So see you next week with more things. Until then, this is me, Lucifer, from a mathematical room. Have a nice day.